So hi, I'm Greg. I work at a company called Formation. We do a lot of fun stuff that I'd be happy to talk to people about. We're always hiring. And this is not really stuff we use. We use Dhall, but the stuff I'm going to be talking about here is kind of what I do in my free time with it, which is not stuff we do at work with it, just to be very clear. So who's aware of Dhall? Like, who knows the name even? OK, that's good, pretty good. And has anyone like used it or familiar with at least its syntax or anything like that? OK. Cool. So Dhall is intended to be a oh, I didn't actually start recording, apparently. I have to click it one more time. There we go. This is now the beginning. So Dhall is intended to be a configuration language, replacing things like JSON or YAML, especially things like YAML. But it does it in an interesting way in trying to be a total functional programming language. It kind of avoids the Turing tar pit of a configuration language getting more and more features until it's just like another programming language with terrible syntax and everything, by giving you everything up to that, just avoiding the Turing completeness and giving you totality and kind of saying like you can do everything you want to do with this language, and it's going to still terminate. You're still going to have things that you expect out of configuration languages as opposed to like Turing complete programming languages. But it turns out that you can do given a total language, you can do anything. And so that's kind of what I try is see what I can do, or like how I have to jump through various hoops to do things that I find interesting. And so let's start with like a little overview of like what Dhall is and what it looks like. This is a blog post written by a coworker of mine, Fintan, that kind of gives a good overview of everything. I'll just to give you some sense of the syntax and things that exist. It has a handful of native types, basically. There's no recursion in Dhall, but there is a list type that is built in that gives you some bit of recursion. And then to look over some of the types, the syntax. So this here is running the Dhall command, feeding it some expression that will be normalized by Dhall, right? So true and false is false. Pretty straightforward stuff. Ors, there's natural numbers. You can add natural numbers. There's integers. You cannot add integers. Integers are basically just opaque data. Same with floating point stuff. They're just opaque. Text is almost opaque, but you can concatenate it. But you can't really do anything else to it. Lists can be concatenated. There's also, you can fold over lists, as in this example here. There's no type inference. So as you can see in this list fold, what it's saying is like, it's going to take a list of Boolean, and here is the list that it's going to fold. And then the result is going to be a Boolean. And then here's the parameters to fold, which are the and for the operation used on conses, and then the nil will be true, right? So standard fold, but again, you have to be explicit about your types.
Great. Do you have to be, I think you just mentioned, but you have to be very specific about what the types of x and y are? Like on the
Yes, yeah. Everything, basically, the function itself needs to know the types. And we'll see when we see what functions look like, you'll see how that works. But you have to be explicit about the types here. And then when you pass, well, you see, I guess if you see a function here, we can look at it. When you pass, this is a lambda, right, that we're passing through. It takes 2 arguments. And yeah, so a lambda looks like this. It actually has a lambda. Dhall auto-formats your code, basically, for you. I mean, it doesn't have to, but you run Dhall format, and it's very nice. It like gives you Unicode things and like re-indents and aligns everything. It's actually been really, really nice to just write code just without thinking about any kind of structure. And when I save it, it all like gets nice and prettified and like looks correct. And I didn't have to do anything to maintain any kind of formatting. So that's very nice. So yeah, so lambdas look like this, where you have some variable and its type, and an arrow, and then the result of it, or the expression you want to evaluate. So let's see here. So yeah, so there's lists, there's optionals, unit, which is the empty record. This is the unit type, and this is the unit value. Records look like this, very similar to JSON, except for not using equals. It uses not using colons for the values. It uses equals. It uses colons for the types. So this is a record type, and records. Here's a value of that type. Oops. Right here. So you can in a very similar way, again, this difference between colons and equals is there, but things that like look fine in JSON can basically be imported almost directly. So you can write stuff that looks basically like JSON and treat it as Dhall with that one syntactic thing, and it just works. You can't do heterogeneous like lists, right? You can't just like mix things in your list. That won't actually be parsed properly. Let's see. So you can project out fields from a record. You can project out sub-records of a record, so there's no row polymorphism. You have to be very explicit about that, about which field you want in which cases. And then there's union types. So this is like a sum type here where you have the options are Monday, Tuesday. This is an enumeration, right? Because all of the values, so each union type has a tag and a value, and the value here is all unit. So this is just a simple enumeration. But you can have, let's see, yeah. So given something like this, there we go, merge, that's what I'm looking for. Merge is basically how you pattern match, basically. And what this means is you have day, which has been defined with that same kind of, this is the type of the union. So it takes a value of that union type and a congruent record that means that has an entry for each option, right? So like for all the different cases in the union here, this record has to have a handler for each of those cases, right? And so that's how you pattern match. And there's no catch-all. It just is like one-to-one. So there's definitely restrictions in this language that, you know, when you're writing your code day to day, like can get in your way, or like don't give you the flexibility or expediency that you want. But that's not the goal, right? It's to basically help reduce duplication in configuration files like in Kubernetes configs and stuff like that, where you can like define a function here and there and just like eliminate a lot of duplication. So it's not trying to just be like, you know, a super like you know, brief or concise some programming language like, you know, like Haskell or something, which definitely there are things that come up that are very not concise. And so now that we've seen all these kind of things, you know, here's a kind of our first FP structure that we're looking at, right, is either, which is just a union type, right, where it has two type parameters used here, A and B, to specify what that is. And let's actually bring that up. So look here, this is this library called, I'll make this bigger, called Dhall which is one of the two main Dhall libraries we use at work. If you look at the folder names, they look maybe familiar. And so you can do lots of things in Dhall, as you can see from these things, including like we have like con extensions and Yoneda. Yoneda has been extremely helpful in Dhall stuff we've written, believe it or not, as has code density, stuff like that. So anyway, lots of FP things. So we'll just take a quick look at either. And actually kind of, it'll give us a little bit of thing here. So either has, the way that we structure everything is in this kind of way. Everything about either is in this folder. The first thing we'll look at is the type. So you'll notice that like there's no names here, right? Like each expression is just its own file. And so you just import files to reference that expression. And you can do like let bindings within your files to give local names, but those names don't escape or live outside of that in any way. So you know, we just refer to either type whenever we want the either type. And so this is just a function. It's a little different than the other ones because its parameters are types instead of like bool or whatever, right? So this is a function that takes two types and returns the type that is the left or right of, you know, what we expect either to be. And yeah, this is just a type level function. It has the same syntax as a value level function, but it works at the type level. And so, again, we have like lots of things here. We have let's look at functor very quickly. The way that we do type classes, so there's no implicits and there's no inference on things. So we have to pass all of our instances around explicitly. We're like, oh, here's, you know, we want to do something with either. Here's the functor instance for either. And so here, this is the definition of functor. Right, it takes some type level function, right, from type to type, which is what a function is, right? It expects a type and then gives you back a type. So you give list expects a type like int and then gives you back list of int as your thing. And so that's the f it takes here, and it returns a record of the operations for that type class. as we call it here. So we're just doing like kind of what you may have heard is what Haskell basically does under the hood, right? Is and Scala and stuff too, where it just kind of passes. It handles dictionary passing for you. We have to do the explicit dictionary passing. And again, map is just defined here as this is for all. And again, this is the auto formatting. You type the word for all, and it substitutes it with the for all symbol when it auto formats. Gabriel likes to use Unicode. I like the Unicode, so happy about that. But yeah, so the type here, map has a type where it takes some function that takes two types, and then takes a function between those two types and returns a function over over the new functor, right? So this is a standard functor that we know, and so we can look at. I was going to look at the either functor, but I'm going to bet that that's not actually a useful one because it's going to just refer to. Oh no, it works. It does it directly, sort of. It refers to map right in here. This is the implementation. Basically, we just import the functor type and the either type, and so basically, we can now say like, given some type A, right, for the left, whatever the left is, we can give you a map that maps over the B to C, takes a function from B to C, and you go from either AB to either AC would be the result type. But you don't have to specify that because that can be. So it's not type inference, right? But it can basically identify that type without any additional context. It doesn't need to use any contextual stuff, so it's not technically inference. And then we use this type annotation here. It's not necessary, but this is basically lets Dhall itself verify that we actually followed the contract of what functor is, right? So like it wouldn't be any different if we remove that, but this will at least cause Dhall to error if we didn't actually define map the right way.
Is there, type is like a general type, right? There's no way to specify, oh, I want a type of like a higher kind of type for this to be able to match. Like I can pass an int and a string, right? That would still.
Pass an int and a string where? Like.
Not here, but
okay.
Example of functor, right?
Yeah.
You're taking in two types, and one has to be like.
Let's go back to the functor. So in the functor, if I can find it again. So this is your this f would be like list, right? So that is your function type. So it is a function from type to type. Like it knows what the kind of that type has to be, right? And these types that are taken in here are just like if you had a list of string, you would pass in like string and then pass int, and then like this would be like length or something like that. And then so you get a list of the lengths of the strings in the original list or something. So it does know those kinds. And in fact, despite Dhall being, this is something, I can dive into it right now. So despite Dhall being a configuration language, it has kind polymorphism. And shortly we'll have a full tower of universes. And so not only can we do things like type to type, but I will just jump into this here. This is the same library. This is a branch that hasn't been merged yet. There's still some things we're trying to figure out, like what's a good way to express. But let's just look at functor really quick, since we were just looking at functor. So this functor is a little different. It's a little more to it. So first, it takes an object of some kind, right? So the actual parameter you might pass here might be type, or it might be type to type, things like that, right? So we now have kind variables. And then we have an arrow, from which takes two of those objects and returns a type. And now we have another. So this forms a category basically, right? Although we don't have the constraint of the category type class here, but we have objects and we have arrows. Are people familiar with the notion of a category or not? Who's not familiar? Anyone want to expose themselves? Okay, so I mean, a category is basically. This is a very hand-wavy way of saying it, but an abstraction over functions where the common category we deal with has objects that are types, and the arrows are functions from, say from int to string, or from bool to int, or whatever, things like that. And so this lets us abstract over that in some way, saying instead of just having like types and functions, we can have like the objects in the category be functors like list or option or maybe or whatever. And then the arrows between them would be a natural transformation, like from which in cats is called function k, which changes an f of a to a g of a, so you can transform that that constructor as opposed to the underlying proper types. And so in this we have this. So now that we can deal with kinds in Dhall, we can define for some objects we have an arrow again, which is like a function in that category, and then we define another category here. So we have category C and category D, and so this has some objects of some kind, and then arrow functions between things of that kind, basically. And now we have our functor. This is the same one we saw in the other place, but now more generic, where instead of just being a function from type to type, is a function from object in category C to object in category D. So this has changed things in two ways, right? So like one, we can now write not just our regular functor, but we can write like functor K or something, which is a functor in the category of endofunctors. Sorry, I didn't mean to say that. But it's a functor. So now we can do like yeah. So we can do functors like one level up basically. But also we can differ what the input and the output categories are, which those are two different things that we couldn't do with the original definition of functor. And the generalized version of map looks basically the same, but instead of having like just a function from A to B, we now say it's some arrow from A to B, and then the result is some arrow from f of A to f of B in a different category. So let's look at like a definition of this. Trying to think of what a good one is. Actually, we'll look at one thing first, which is like, so the regular functor we see in Scala and Haskell and everything, the thing that's called functor is really an endofunctor, which means it's a functor where the result category is the same as the source category. So here, that just happens by being, so this is referring to the general functor type that we were just looking at. The dot dot means it's the director level up. Not my favorite thing, but this is just the way imports and files work. But this, you give a single object and a single arrow, so one category. And you're saying here that like the functor has both the same source and destination category. So this is just like a type alias saying an endofunctor is a functor where both categories are the same. Right, and so let's see. Other fun. Let's look at categories a little bit since we're kind of talking about that. So categories. We have simple categories that are just, so the simplest one isn't not in there, which is just function. This category is it's just a function. It's something that takes two types and returns a function between those two types. Or not, doesn't return a function, but the result type is a function between those two types. So this is just like currying the function thing, because you can't actually, operators are not curryable in Dhall. Otherwise, you could just write this as like just the arrow or something. But we have to make it curried. But we have other categories that we can play with. Common categories, often called Kleisli. I didn't use those names. I'm still wishy-washy about what the right name is. I called it star here, which is not great because it's not a star category. But the thing is that it's actually broader than just Kleisli. You don't necessarily need a monad instance, which is what Kleisli says. Like for something to be truly Kleisli, it needs to be on a monad. But anyway, this is another category where, again, we're abstracting over the category. So we have objects and arrows in some category. Here's the monad itself, which is basically a function from that. You can often just think of like object as being type and arrow as being a function, and then you can ignore those top parts without abstracting over the category. So this could be type to type. If we hadn't abstracted over categories here, then it takes, say, two different types and gives you a function back where the result is wrapped in that m, right? So now you have a function, you have an arrow a to b, but what it really means is you have a function from a to m of b. And so by abstracting over the category, we've managed to make that monad part of the arrow, part of the function part, as opposed to part of the either source or destination type. If that makes sense. And so that allows us to abstract a bunch of things over monads, basically, that normally would just be regular functions. And actually, I'll talk about that a bit tomorrow with how traditionally, like you'll define some function like, what's a good case? I don't know, like foldr or fold right, and then like fold right m, right? You end up with like these duplicate definitions where the variation is just like, oh, and I'll do it in a monad. When really those aren't actually different things. If you can abstract over the category, you can define that once, and then if you specialize it to the category of types, you just get fold right. And if you specialize it to a Kleisli category, you get basically fold right m. And so those things unify, and that's kind of the point of doing this kind of categorical abstraction, is that unification of many disparate things. You now have very few are. Did you?
Yeah. Did anybody review that pull request? Say, I see that commit message like that.
Yeah, no one has reviewed this. This is still on a branch. Yeah, definitely with dealing with the kind polymorphism stuff and all the categorical parametric stuff, I just was like, oh, I wonder what happens if I do this. I wonder if it works if I do this. Oh, this works, cool. And I was like, commit it. Just like, so yeah, it's very it's very fast and loose on this branch.
Formation does squash merges, so they won't be on the
Yeah, exactly. No one will see this in the end. Yeah, and so there's a bunch of other categories. I don't have to go into the implementations of all of them, but there are the opposite category, which is where an arrow from A to B is actually the function from B to A. So it reverses. So if you're like contravariant functors is a functor from an opposite category to the original category. So you get, if you have a function from B to A, you can go from f of A to f of B. And so it just reverses that. And so you can, and the way that this works is that, this works for any category. So it takes an input category and reverses that input category. So it's not specialized to functions, right? It actually takes the category that it should take the opposite of as a parameter. Other categories, dagger categories, are basically like invariant functors, where they're kind of considered categories where there's no direction to the arrows, right? Normally you think of like a function from A to B. But in a dagger category, any function or any arrow from A to B, there also has to be a matching arrow B to A. So like isomorphisms, basically, a category where the arrows are isomorphisms instead of just functions. So it removes the directionality from the category. And that's how a invariant functor works, right? You now have an invariant functor is a functor where you provide it both a function from A to B and a function from B to A, and that gives you a function from f of A to f of B. So you need both directions. And so that's a functor from a dagger category to whatever the underlying category is again. So all these things can just be done in this configuration language, because you definitely need this stuff to write your config files. But this is what's so neat. Like this language is extremely restrictive, right? Like again, it's total. The language does not have recursion other than on lists like built into it, and you can't just define in your normal recursive way arbitrary things. And so with all this restriction, you can still define all these things, and none of these things care about recursion in any way, right? These are all pretty flat structures. One last category I'll talk about here real quick is a monoidal category, which isn't actually. So this is sort of the same thing. It just adds extra structure. So basically, given some objects, you have arrows between those objects, as we've already been seeing. But it adds in a very monoid-looking thing, right? With a monoid, you have, given two things, how do I combine them? And also, how do I get a thing out of nothing, right? Like here's some identity object. And that's why this is called a monoidal category, because you can see here's the identity, which is some object. And there's a product, which takes two objects and combines them to give you a new object in that category. The most common case of a monoidal category is the Cartesian category, or on set, where your product is just a tuple, and your identity is the unit type. And so this is a very useful category. We'll see in a minute. There's also co-Cartesian, much less useful, but the product is either. The product is either, right? This is very abstract-y things. And then the identity is void, so this is the empty union type, right? All the alternatives, just zero alternatives, so you can never create a value of that type. So now that we know about monoidal categories, we can look at a monoid. So this isn't going to be the most precise description. Is this big enough for everybody? Like now that I'm 3/4 of the way through here. So in a monoidal category, for a monoid, this is a very abstract monoid, right? This is like given an object in some category, which has to be monoidal, so it needs that structure of products and identity in the category, right? So this is saying for some monoidal category where the objects are, whatever this object is, you have an object which has identity, which this is doing is extracting the identity and arrow things out of that monoidal category structure I had shown before, right? So now you have an arrow from the identity thing, which is, say, in the case of set, unit, to an m. So basically just like give me the default or identity m, empty list, or empty list, or 0 for addition, stuff like that. And then it combines it with semigroup. This is a type. This is the record combiner, the record type combiner, really. This double triangle sort of thing. And so this takes this field or this record and combines it with whatever record comes out of this, which is the combine or append operation in semigroup. But I won't get into that. But anyway, you can see that you can define a monoid if you have this monoidal in a monoidal category. And so using that, we can do all the usual fun things. Like here is you may be familiar with this one. A monad is a monoid in the category of endofunctors, right? So this is monad. You can kind of ignore the first part. This F is really, that is your monad. So it might be like list or whatever. And here you're just specializing monoid. Here's a monoid, but you're specializing it to a category where the objects are functors, and the arrows between functors are natural transformations, and the product is composition. So like f of A. And the identity is just pure, basically. And so that's this is just implementing, right? A monad is just a monoid in the category of endofunctors. That incomprehensible statement. It turns out that there's also let's get to it right here. This is an applicative is also a monoid in the category of endofunctors. The only thing that's different really is that instead of using composition as its product type, it uses what's called deconvolution, which basically looks like, what's it called in Scala? Like lift 2? Is that what people call it? I don't know. So like lift 2, where you take like an f of A and an f of B and a function from A, that takes A and B and returns you a C. That's what deconvolution is, just like as a abstracted structure is that thing. And so when you have deconvolution as your product, you have an applicative instead of a monad. So again, both just monoids in the category of endofunctors. And again, this is like weird stuff, just kind of showing off like what you can do in such a restricted language. Other things you get for free, like rank n types, just fall out of the simplicity of Dhall, and which has been very helpful for things because you need you don't have existentials. So if you want to do anything with existentials, you need to take advantage of rank n types to be able to kind of emulate. I don't know if that's the right word. Existentials using universal types, like for all. And so we can fake existentials basically, and we do that in a bunch of places. Actually, deconvolution might do it. Let's see. Oh, it's way too deep. So deconvolution is implemented as a left con extension. One of those basic types that Let's see if we can see it in here. Yeah, here. So this is an existential. So what this is doing, ignoring everything else around it, is basically this is declaring B as an existential type. And you have to do that by kind of like wrapping it in an additional function that takes some result type that, given a function that takes a B, like you can like do all this stuff. So this basically inverts the for all into an exists. But it's super ugly, right? Like this whole thing should be like this very tiny, not very tiny. I guess it should just be like this part, pretty much, but like with an exists or something. But we can't do that. That doesn't exist in Dhall. So you get very ugly stuff dealing with existentials. But yeah, so this is one of the two libraries we use. And again, it gives you like everything you see in cats and stuff like that, and in very abstract ways, right? Where you actually get kind polymorphism on like everything and different category parametricity. Which has been, it's been really cool to be able to like define things like monads in such a, like an abstract way, and just say like it's a monoid in this way. We use another library. I mentioned that Dhall doesn't have any recursion. Thankfully, that is like a specialty of mine. So we wrote another library called Dada, kind of referring to the Dadaist art movement, because it is just insane that you would need to do this. But there's no recursion, so you can still define recursive data types using fixed point operator recursion schemes. Is anybody familiar with recursion schemes? Who's here? Good, got a few hands, good. But what they allow you to do is basically encode recursion. As long as you have higher order functions, basically, you can encode recursion without actually having recursion provided to you. And the nice thing, though, is the recursion you get out of this is total, right? Like if you use this particular type mu, which we don't really have to read about what it is, but if you use this to give you your recursion, you're guaranteed that your recursive structures are always finite. You know, like in Haskell, you have this possibility of things can always be infinite because of laziness. But this guarantees that everything will be finite that you deal with. And you can still deal with infinite values in a way, which is this other type, which is existential, so is ugly. It has that same existential pattern on the bottom line there. But this allows you to create potentially infinite structures by basically just building it as a delayed function. That here's the delayed function, and then here's like what you would apply to that function. And so you can like step through the structure, but you can never fully evaluate it. You can never get Dhall to say like just run it to the end, because that wouldn't be total. That would like potentially run forever. But you could step through it for some fixed number of things, or you can just like evaluate to this as the final result of your thing, and have the interpreter, say Haskell, if you're using this from Haskell, actually do the evaluation. But you would know from the type that this is potentially an infinite value. And so you now have that notion of partiality, of like maybe non-termination existing at the type level. And it has to exist at the type level. There's no way within Dhall to erase that. So you always have that promise of like, we know this will terminate, or we can't evaluate it, but we can say that this thing might not terminate. And this too has branched the same way as the other one. There's now this whole category polymetric or parametric version of recursion schemes here, where here's your catamorphism. Given an A, which is an object in the category, you take an arrow from this is the pattern functor of A, and for people who are familiar with recursion schemes, and it gives you an arrow back that folds the whole structure down. And again, category parametric. So now this collapses. For people who are familiar with recursion schemes, there's like, I would say what are called, or what I would say is simple recursion schemes, and then like there are ones where they carry type information around that allow you to restrict what types can be used at each step in the recursion. And so this collapses both of those into one implementation basically, and allows you to again eliminate a lot of code. So we actually use this at work, not the kind polymorphic stuff, but we do build recursive structures in Dhall using this to allow us to express some of our configs. Although most of the complexity is not exposed to the people who are writing the Dhall configs. Yep.
Please tell me if I'm jumping too far ahead. Can you show a few examples of?
No.
Okay.
No, I can't. No. Let's see. Is there a particular example or a particular thing that?
How you actually use it, like in your day-to-day?
Yeah. Okay. Let's see here. So one of the things we use it for, and I'm trying to think of a good thing. So basically, the way that we use it is we kind of build up a library of these expressions, of these functions, so that the end users just use that library in the end. Like they're not really using a lot of this stuff. They're using things that are like more complicated functions that encapsulate a lot of information, but they don't see those details. So I'm trying to think of something that is small, but let's see. I wonder if we have. Let's go back to this. Yeah, I don't have a good example for that, but there is. I'll totally. Is this the right one? I think there's two, and one of them is. Yeah, this is the right one. So this is Dhall Kubernetes. Might have some good examples of things. Yeah. So here is basically a. This is the Dhall config, and it outputs that Kubernetes config, right? So it already is wrapping up a bunch of stuff in a smaller thing, right? So this is referring to external expressions here, like this default and default container here, that take these parameters and expand into some, basically larger thing where it basically just has a bunch of default values for different fields in the Kubernetes thing. So you can use that repeatedly. There's other. Let's see, this one, and this uses a lot of let bindings, right, importing lots of different things, so you can refer to names. That one seems like counterproductive, right? Like, that's the full Kubernetes, and the Dhall is a little bit bigger. But anyway, it's really good for like when you have kind of many services with a lot of similar configs between them to define that once with maybe like a name parameter or something like that and just like apply that same function over and over again. But this Kubernetes use case is really useful for, because Kubernetes configs can be super hairy and big and it allows you to like pull those into small functions. So I definitely recommend like this library. I don't recommend the libraries I've been showing you this whole time. Those are totally just fun and experimental and like see what crazy stuff we can do in a language that is intended to be super restrictive, right? And that like really, you need so little stuff in order to be able to do everything. It's kind of crazy that like you can actually, that's kind of the point is like it's crazy that you can do all that stuff in a language that's designed to like be so restrictive. But the restrictions do give you extra promises, right? Like you have this proof, this promise of totality through the whole thing. And it does mean that some things become more complicated to implement or whatever, but in the end, you have some guarantees that come out of that. Yeah, I'm trying to think of something that I have that, like anything that I would show you from what we use it for at work is kind of either exposes some things that I probably shouldn't expose or has enough layers of indirection in it that like seeing the things that come out of it is not particularly helpful. But I do recommend Dhall in general as a configuration language. I also recommend it as a very fun thing for experimenting with like language features. Like the language implementation is so small. I implemented kind polymorphism, which sounds like a crazy thing. And I've looked at the kind polymorphism implementation in Scala C, and it's super complicated. Like I couldn't understand it, I couldn't do anything, but I could implement it myself in Dhall in about half an hour because the language is just so small, so simple that like the places that have to change, you make one change basically, and everything else just falls out of compiler errors. And be like, oh, I need to update this to handle this. I need to update that to handle that. And you're just like, it's like everything is very clear. Everything is very straightforward. So it's definitely a great language for experimenting both within and around. But yeah, that's sort of crazy things you can do with Dhall. The end.